In this video, we'll look at some examples converting back and forth between numbers in base 10 and other bases such as binary base 2, octal base 8, and hexadecimal base 16. And here are the examples that I'm going to go through. Let's start with example 1. It says write 20 in base 2, and because I want to go to base 2, I'm going to look at increasing powers of 2 beginning with 2 to the power 0, 2 to the power 1, then 2 squared. I'll keep going as long as I have a value that is less than or equal to what I'm trying to convert, which in this case is 20. So we're at 8 now. That's still less. So 2 to the power 4 is 16. 2 to the power 5 is 32, and that's greater, so I won't need this. It's too big because 2 to the power 5 is more than 20, and I won't use it in my calculation. Now let's look at what each of these values are. This is 1, 2, that's 4, and 8, and 16. And ultimately what I'm really just trying to do is to figure out how many of each of these powers of 2 would you have to add together. How many of each one would you add together to make up 20? You answer that question by long division. So you start always with the biggest power of whatever base you're working with. In this case, it would be 2 to the 4, which is 16. See how many 16s are required to add up to make 20 or to equal 20, and you do that by division. So 16 goes into 20 once. 1 times 16 is 16, subtract, and so there's 4 left over. So then you just take that remainder and figure out how many of the remaining powers of 2 are required. So in this case, how many 8s do you need to add up to 4? Well, none, right? And you get that answer by saying 8 goes into 4 how many times? 0 times. And then you can complete this. 0 times 8 is 0. Subtract, you get still the 4 remainder. So we're just moving on to the next lower power, which is 4. Say how many 4s do you need to add together to get 4? And you just need 1, because 4 goes into 4 one time, and 1 times 4 is 4. That gives me a 0 remainder. So then I'll write down that 0 remainder. Now, just to sort of continue my algorithmic process of doing this, I'm going to follow, but I can sort of tell the answer, but I think generally it's good to complete all the way to the lowest power because that's really how you can read your answer clearly. So if we continue, we're going to look at the next power down, which is 2. 2 goes into 0, 0 times. 0 times 2 is 0. And that's another 0, and then I get that remainder, and take the next lower power, which is 1. 1 goes into 0, 0 times. That is 0 divided by 1 is 0, and 0 times 1 is 0. Subtract 0. Now I have to go through the sequence of all of the powers down to the smallest one, and then once you've done that, you will always get a 0 remainder at your last step, unless you made a mistake. And so then you can read the answer right off of these quotients here. Notice that my answer is all 1s and 0s, and that's because I'm in base 2. You won't ever get a 3 or anything 3 or bigger when you're in base 2. It'll just always work out that the numbers are 0s and 1s if this is done correctly. And so we can see the answer now just reading off these quotients. 20 in base 10 is written 1, 0, 1, 0, 0 in base 2. So use a little tiny subscript to indicate the base if it's a non-standard base. If you don't have the subscript, it's understood to be in the standard base 10. So this is the answer. Let's move on to the next one. I'm going to write 229,638 in base 8. And so now we're working with base 8. We'll look at powers of 8. Powers of 8 starting with 8 to the 0, 8 to the 1, 8 squared, 8 cubed. I might need a calculator to keep track of these. I'm looking for continuing as long as I have values that are less than or equal to 229,000. So 8 to the power 3 is 512. So this is still much less. So I know I've got to keep going. 8 to the power 4, 4096. Got to keep going. 8 to the power 5, 32,768. Okay, let's try one more. 8 to the power 6. That's 262,144. And so I don't need that because that is bigger. It is bigger than the 229,000 I'm trying to convert. So we wouldn't need any of these because even just having one of those would add up to more than what we're trying to convert. So we really only need to go up to 8 to the 5th, right? Use powers of whatever base you're converting to up as long as it's less than or equal what you're trying to convert. Okay, so this is 1, this is 8, and this is 64. And we'll start always with the biggest power of whatever base as long as it's less than or equal to what you're trying to convert. So 32,768. 32,768. How many of those do you have to add together to add up to 229,000? 229,638. Well, this is definitely something that you want to use a calculator to speed up. So we'll take 229,638 and divide by 32,768. It goes about 7 times, but not exactly. So 7 times 32,000. So then multiply that. 7 times 32,768. And you get 22,9,376. So then subtract that. We get 262. With the 262 remainder, I would then move down to the next lower power, which is actually this one. So 262 divided by 4096. Well, obviously 4096 is much bigger than 262, so it goes 0 times. You won't need any number of this value. So 0 times 4096 would of course be 0. Subtracting means that I still have the 262 remainder that I need to go to the next lower power, which is the 512, which also is larger than 262, so that's another 0. 0 times 512 is still 0. So I still have the 262 remainder. So I'm now going to use the 262 and divide by the next lower power, which is 64. 64 does go into 262, so we'll just use a calculator to speed that up. 262 divided by 64 goes about 4 times. And 4 times 64, that's 256. We'll put 256 there and subtract. So the difference there would be 8. Sorry, actually the difference is 6. Right, so then carry the 6 to divide by the next lower power. The next lower power would be the 8. 8 is bigger than 6, so that goes 0 times. 0 times 8 is 0. That gives me a 6 remainder. Still have the 6 remainder. I want to divide by the next lower power, which is 1. 1 goes into 6 exactly 6 times. 6 times 1 is 6. Subtract, that's give me a remainder of 0. There's the 0 remainder on the last power, which is what I need. So now we can read off the answer. The 7, the 0, another 0, the 4, a 0, and a 6. 229,638 in base 8 is 700406, and then put a little subscript 8. Okay, example 3, 888,847 in base 16. So I'm working with base 16, so I'll look at powers of 16. So this is 1 and 16. This is 256. What's 16 cubed? 16 cubed is 4096. 16 to the power 4. That's 65,536. 16 to the power 5. That's actually 1,048,576. So that's clearly larger than the 888,000. So we don't need this one, it's too big. So we'll start with 65,000 and divide that into the 888,000. How many times does 65,536 go into 888,847? Definitely use a calculator for that. Goes 13 times with some left over. So multiplying, I get 851,968. And then subtracting 36,879. So we take the 36,879 remainder and divide by the next lower power. We've done this one, so now we go to that one. Take that remainder, divide it by 4096, goes 9 times. 9 times 4096, 36864. Subtract. That's 15. Take that remainder of 15. Now that I've done this one, I go to the next lower power, which is 256. Now 256 is bigger than 15, so it goes 0 times. I still have a remainder of 15, so then I'm going to divide by the next lower power. Because we've just divided by 256, we're done with that. We go to the next lower power, and that's 16. And I'm copying the 15 up here and dividing by the next lower power. So 16 goes into 15. Also, that's 0 because 16 is larger than 15. 0 times 16 is 0. Copy that. So no, 15 minus 0 is 15. So I take the remainder, divide by the next lower power, which is 1. 1 goes into 15. 15 times 1 is 15. And 15 minus 15 is 0. So now we can read off the answer from these quotients. But we're using base 16, and so we've got 1, 2, 3, 4, 5 numbers to write down. 1, 2, 3, 4, 5. But each of these will represent a larger power of 16. And if we wrote something with 2 digits, then it would itself represent 2 different powers of 16. So we've got to find a way to capture 13 with a single character. And that's why we use letters. So once you pass base 10, you need to start using letters for numbers that are bigger than that are 10 or bigger. So the standard thing to do is to use the letter A to represent 10, but carry only one position or one character. Use 11 for use B for the number 11. 12 we'll write as a C. So 13 we'll just write the letter D. 14 is E. 15 is F. So this is where I would put 13, but instead of writing a 2-digit number, I'm just going to write the symbol D. And then I can write 9, 0, 0, and then the last is 15, which I will use the symbol F. And then the fact that it's base 16, we indicate like that. So 888,847 is D900F in base 16. So if you think about base 2 was only zeros and ones, and let's say base 8 is only the numbers 0 through 7, just like base 10, the standard base uses digits 0 through 9. When you go to something like base 16 or any base that is 10 or bigger than 10, you have to have that many different symbols to work with to write the number. So if we're in base 16, we actually have to have 15 different symbols to represent the numbers. And so that's another explanation as to why these letters come in when we're above base 16, is because we have to be able to represent with one symbol each of those 16 different numbers that occur in base 16. Example 4 says just write the number 15 in base 16. And this is to the point that actually 15 is less than the actual base. So we're going to just write, the answer is just going to be F. Let me see if I can show how that would work if you were writing out steps. You would begin with the powers of 16. So we have 16 to the 0 and then 16 to the 1. But that's obviously 16, which is bigger than the number I'm trying to convert. So even that 16 is too big. We wouldn't need it. So we just look at how many, we're basically in the ones place when we are writing 15. Only need to take one single character, right? So in other words, you'd say 1 goes into 15 how many times? 15 times. 15 times 1 is 15. So that's it. That's the whole answer. But if you wrote 1, 5, it would mean two different place values. So you just say 15 is just F in base 16 because I'm using this scheme of using the letters to represent numbers 10 and larger. So let's write the number 10, which is in standard base 10, actually in base 9. So since we're writing in base 9, we need to look at all the powers of 9. 9 to the 0, 9 to the 1, 9 squared. Well, that would be 81, so we won't need that one. 81 is bigger than 10, so don't use that. We just have the ones place and the nines place to think about. In other words, how many ones and how many nines. So begin with the largest power of your base that you need that's less than or equal to the value you're converting, which is in this case 9. So we'll say 9 goes into 10. How many times? How many 9s do you need to make a 10? And the answer is just 1. 9 goes into 10 one time. 1 times 9 is 9. Subtract, you get a remainder of 1. So then take that remainder, divide. We got the 9 done. Let's divide by the next lower power. That's 1. 1 goes into 1 one time. 1 times 1 is 1. And there's the remainder 0. So this is the answer, 1, 1. So 10 is equal to 1, 1 in base 9. What you're really saying here is that it is 1, 9. This is 1, 9 and 1, 1. A 9 and a 1 makes 10. Or a 1 in the ones place and a 1 in the nines place. So now let's do some conversions that go the other way, that take some arbitrary base and convert it to the standard base 10. Now looking back at the first 5 examples that I've done, I've always been converting from standard base 10 into some other arbitrary base, and all of these required this long division. If I was converting into base 2, I had to look at all the powers of 2 and then divide by those powers of 2 using long division to figure out all these quotients, and that's where I got the answer. It was all this division when I'm converting to the base 2, or if I'm converting to base 8, I did all this division with powers of 8. And this was a converting to base 16. I'm doing all this division with powers of 16. Here I'm doing a division with a power of 16. Here's division with powers of 9. So converting to some other base means you do long division with powers of that base. But if I want to go back to base 10, I just need to do multiplication. I just have to read how do we interpret the meaning of this expression if it tells us it's base 2. The answer to that I might be able to explain if I write it out again. If I have 1, 1, 0, 1, 1, 0 in base 2, we look at this as the ones place, this is the twos place, this is the 2 to the 2 place, the 2 cubed, the 2 to the 4th, the 2 to the 5th, and it would go on if we had more digits. So we could just write the place value right above it. We'll say this is 2 to the 0 place, which is really the ones. This is the 2's place. This is the 2 squared place. 2 cubed, 2 to the 4th. This is the 2 to the 5th place. So you can say we have 1 in the 2 to the 5th place. We have 1, 2 to the 4th. There are no 2 cubes. I'm reading down from the biggest one. So I have no 2 cubes. I have 1, 2 squared plus 1 in the 2 to the 1 place plus 0 in the 2 to the 0 place, or just in the 1's place. So that means we're going to get 132, 116, 0 times 8, 1, 4, 1, 2, and 0 ones. So adding that up, 54. 110, 110 in base 2 is equal to 54 in base 10. Okay, now let's write this number 5a E73 in base 16 converted into now base 10. So we're going to switch from base 16 to base 10. So recopy it, 5a E73 base 16. Each of these is an increasing power of 16, where the letters represent numbers bigger than 10 or bigger. So this is the ones place, which is 16 to the 0, 16 to the 1 place, 16 squared place, 16 cubed, 16 to the 4th. So we have 5 in the 16 to the 4th place. We have a, which is actually 10, in the 16 cubed place. Because e is 14, I have 14 in the 16 squared place, 7 in the 16's place, and 3 in the 1's place. So that's 5 times 16 to the power 4, and 10 times 16 cubed, 14 times 16 squared, 7 times 16, and 3 times 1. So 5AE73 in base 16 is 372,339 in regular base 10. Okay, this one works just the same way, but it's base 8. So because I'm switching into base 10, it'll be just multiplications of all the powers of 8, where each of these represents how many powers of 8 we will expand. So we have 3, 4, 7, 1 in base 8. So this is the 8 to the 0 place, 8 to the 1, 8 squared, 8 cubed. So 3 times 8 cubed, 4 times 8 squared, 7 times 8 to the 1, and 1 times 8 to the 0. So that's the answer. 3471 base 8 is 1,849. Make sure you don't say 3,471 because this is not base 10. This is not a thousand's place. Of course, it's the 8 to the 3rd place. It's the 512 place, and this is the 64's place, and this is the 8th place, and this is the 1. So don't use the word thousand or hundred or tens or in here. We just say 3471 base 8 is 1,849. Okay, last example. Write the number 1001 in base 9 in base 10. Or let's say write the number 1001 base 9 in base 10. Because what I have is already in base 9, I know that these are values in base 9, and I know that the place value is a base 9 place value. So this is the ones place, but that's base 9. So that's the 9 to the 0 place, 9 to the 1, so 9 squared. That would be the 9 to the third place. We have 1 times 9 cubed. We have no 9 squares, no 9s, but when we have one single 1, we have 1 in the ones place. 9 to the power 3 is 729, so we have 729. Let's say 729 plus 0 plus 0 plus 1. So 730, that is 1001 in base 9 is 730 in base 10. All right, that's the last example. I hope this has been helpful.